with those physical dimensions. In the last quiz, we had calculated the neutral axis. Neutral axis was 6.04 centimeters from the baseline. This is a neutral axis, and that distance from the baseline was 6.04 centimeters. Some of the other things we know is that we were going to apply then a moment of minus 12,000 Newton meters. We know the material was aluminum 1100. We know that for pure bending, the only thing we have to worry about is plane stress. So we're always interested for safety in that yield value. And that yield value was 95 megapascals. If we go back and look at the member, so I'm taking this from this view, turning it 90 degrees so you're looking at it on its side. So you see these two lines that correspond to those two changes, where this is the length of the member, and we're applying a negative moment, which means the moment wants to make it frown. We know the value of that is 12,000 Newton meters. And notice we do not put the minus sign here because we're letting the vector show that it is minus. When you do that, you automatically know that the top of this is in tension, the bottom is in compression. I would go over here in this view and do the same thing where this is in tension and this is in compression. And just looking at this, you can see that this point is the furthest from the neutral axis. It's compression. So this point is going to be the maximum value for compression. We don't know what it is yet, but we know that it's going to occur there. If we look at the top, we know that that distance up to here is going to produce a maximum value for tension. We know that the formula we use to find plane stress anywhere throughout our structure is equal to my over I. And in particular, y is the distance from the neutral axis to a point of interest. So in looking at this distance to get to sigma max for tension is greater than this. So we know that sigma max for tension is going to be sigma largest value. And this is the one that we're going to compare to sigma yield for safety. Because if this system fails, the first place it's going to fail is right at the tip of the triangle, which in this view would be right here. In this view, you would be along that top line. Any questions on what we did so far? Justin, did you have a question?
I have a question about what is, so we need to draw a free body diagram of the system. So is that both pictures that you've drawn, or is it the one on the right? That's the free body diagram.
The free body diagram, this is the free body diagram right here.
Okay, thank you.
Somebody else had a question? Ty, did you have a question?
If you're talking to me, that was my question about the free body diagram.
Okay. As soon as you show this moment, this is a free body diagram. You can't really see it in this view from the way it's done. Because if you go back and look at what you're doing, in this view, with this, you're basically making it distort. To look like that to get your frown. So it's frowning here, but when you turn it sideways so that you're looking at the cross section, you do not see that frown, if you would. All you're seeing is the cross section as presented. Okay.
And would we put the neutral axis into the free body diagram to represent where that is, or?
Yes.
Okay.
Remember, this is the free body this is the cross-sectional area. We have calculated the neutral axis looking at the cross-section because the definition of neutral axis, it locates the centroid of that cross-section shape. So the centroid is along this neutral axis. When we turn this sideways, so that you're looking at it in this view, remember this neutral axis will also show up here. It is also 6.04 centimeters from the base because this is your baseline. So the baseline here reverts to a line here. So you're still measuring that distance 6.04. Because remember, the neutral axis is a plane. It goes through the member completely in this direction. And you look at it here, it goes through it at this direction, both of which are 6.04 centimeters from the baseline. So in this view, everything above the neutral axis is in tension. In this view, everything above the neutral axis is in tension. In this view, everything below the neutral axis is in compression. In this view, everything below the neutral axis is in compression. But typically, when you're looking to see what's going on with the stress at any particular location, you're going to use this view. If there are no questions on that, what I'm going to do is spend the rest of the time solving the problem. So we've established the neutral axis from our last. We know the particulars about the material in question, so I'm going to erase this. We know that for any point, the plane stress, which is a vector, is equal to the moment applied, which is a vector, times y divided by I, where this is the applied moment. This is the distance from the neutral axis to a point of interest. This is the rectangular moment of inertia. And the result will be plane stress. And as long as you use links in you're taking centimeters and putting it into meters. So centimeters, if it was 2 centimeters, it'd be 2 times 10 to the minus 2 to get it into meters. As long as you use length in meters, the numerator, which will be times 10 to the minus 2, the denominator, which is going to be 10 to the minus 8th, you'll end up with 10 to the plus 6th in the numerator when you do the canceling, and this is automatically mega, and so your answer will automatically come out in mega pascals. Okay? So, if we go back now and do some calculations, we need to find I for this shape, and we know that I is equal to the summation of all the I sub 0 plus AD squareds for how many number of sections you have. So I would go from 1 to n. In this case, we have 3 sections. So we're going to need to do 3 of these calculations. So you're going to need to do I sub 0 plus AD squared for my semicircle. We're going to need to add to that I sub 0 plus AD squared for our rectangle. And then finally, we need to add to that I sub 0 plus AD squared for our triangle. Okay? So, where do we find the I sub zeros? This is the basic rectangular moment of inertia for the shape. So you would find those in the second page of the 3-page handout that I gave you before. So if we do this for the semicircle, I sub 0 is equal to 1/8 pi r to the 4th plus the area, which is 1/2 pi r squared, times d squared. And what is d? D is the distance from the neutral axis to the centroid of that section. So the neutral axis is at 6.04. The centroid of that particular section was 5 minus 4 times the radius divided by 3 pi. So you need this quantity squared. And then for the rectangle, that's going to be plus 1/12 the base times the height cubed plus the area, which is the base times the height, times that d value squared, which is going to be 6.04 minus, it was 5 to get to here, and then 3 more there, so that's 8 squared. Then you have to do the triangle, which is 1/36 the base times the height cubed, plus the area, which is 1/2 times the base times the height, times its d, which is the distance from the neutral axis to its centroid, which was 5 plus 6, and this happened to be h over 3, and that total thing came out to be 12.33. We're going to square that. So we've accounted for the semicircle, the rectangle, and the triangle. And I had that value come out to be 1367.8 times 10 to the minus 8 meters to the fourth. You might get some slight variation here depending upon how you round off certain numbers. But this number is a constant for this cross section. So as long as we're talking about this shape, this is a fixed physical property of that cross-section shape. Any questions on what I did there? Again, you might get a little bit of a variation there. Excuse me. Excuse me. When you originally worked the neutral axis, you'll find out that you used this value when you calculate the neutral axis. So if you're just working it on your calculator where you're just plugging numbers in and you're spitting out an answer, I'd encourage you to list everything, because when you use it in this calculation, you're going to find out that you need to find that number again, and you want to be consistent that you use the same number. Okay, once we have that value, we can go back now to our base equation for plane stress. We know plane stress is equal to the moment applied times y divided by I. And in particular, I asked you what was the value for the maximum plane stress for compression. So this is going to be the applied moment. Notice we do not have to put the minus in here, because we're going to automatically know that everything below the neutral axis is in compression. So you don't need to use a plus or minus when you're putting in the moment value. The y value is the distance from the neutral axis to the point of interest. So that is 6.04 times 10 to the minus 2 meters. And what is I? I is the physical property we just calculated. Notice cancel, cancel. This is going to come out to my negative 10 to the 6th. So for the maximum value for compression, that value comes out to be 53 megapascals. And because it's below the neutral axis, because that is compression, I need to put a minus sign there. Let's say I then go up and I want to calculate sigma max for tension. We're going to use this exact same equation. The applied moment is still the same. The rectangular moment of inertia is the physical property of the cross-section. So the only thing that changes is this value. So if we go back, this is going to be 12,000 Newton meters divided by 1367.8 times 10 to the minus 8 meters to the fourth. But what is this distance? This distance is the distance from the neutral axis to the top. And that value I had be 8.96 times 10 to the minus 2 meters. So you can cancel, you can get your 10 to the 6th. And I had this value for maximum be 78.7 megapascals. We now know the maximum value for plane stress for tension. It's this value, and it occurs right here. We know the maximum value for compression, which is this amount, and it occurs right here. So we can immediately do our safety analysis. Sigma yield for my aluminum 1100 was 95 megapascals. This is a maximum value that's below, so my system is safe. Any questions on what we've done so far with that?
Professor, when we do our conversions to megapascals, we need to convert it to meters first, or can we do it in centimeters? Which value should we use? 'Cause I had in my note for centimeters, and I think that was wrong.
You're effectively doing it in centimeters, but you're using the correct units and powers of 10 to make that happen. So for example, let me use this as an example. So we know that this distance is 6.04 centimeters. So when I plug in this value for y, is 6.04 centimeters, but that is also 6.04 times 10 to the minus 2 meters. As long as you use this 10 to the minus 2, every time you're putting in a centimeter value, that makes it into meters so that you will have the desired 10 to the 8th here, 10 to the minus 2 in the top. So when you bring this up, it's 10 to the minus 2 times 10 to the plus 8, which is going to be 10 to the 6, which gives us our megapascals. So you can do all these calculations using your centimeter value. Just realize what the powers of 10 are that are to your advantage that makes it come out in megapascals. That answer it, Chris?
Yes, thank you.
Okay. Any questions on the safety calculations we just did? Okay, the next thing I asked you was, what is the plane stress at point A? So I can go back and say, what is the plane stress at point A? So this value is still 12,000 newton meters. Again, you don't have to put in plus or minus because we've already defined what's going to be tension, what's going to be compression. The I value is still the same because, again, that's a physical property of the cross-section. So what is my I value? The I value is the distance from the neutral axis to the point of interest. Have your baseline. You know that from here to A is 5 to here, another 6 to here, so it's 11. From here to here was 6.04. So that difference is the distance from the neutral axis to the point of interest. So when I multiplied this value times this value divided by this value, that value I had come out to be 43.2 megapascals, positive because it's in the tensile part. And in reality, when you stop and think about that, anything along the line of this side of the triangle is exactly the same distance from the neutral axis. So any point along that line has exactly this same plane stress. The next thing I did was I asked you, What about a point right here, which we call B? So in this case, I'm going to drop down here. And let's look at point B, which again is right here, excuse me, right here, which is where the rectangle attaches to the semicircle. So, same equation, moment is still the same, I is still the same. Now we need to find y, which is the distance from the neutral axis to the point of interest. And again, that's nice to have the baseline, because from the baseline to the neutral axis is 6.04. From the baseline to this point is 5. Okay. So this distance is 1.04 centimeters, or 1.04 times 10 to the minus 2 meters. This stays the same. So my plane stress for point B was minus 9.13 megapascals. And again, it's a minus because point B is below the neutral axis. We know everything below the neutral axis is in compression. And again, anything that's on this line with B, because anywhere along that line has the same distance from the neutral axis, is going to have exactly this same plane stress. Any questions on how we found plane stress for A and B? Justin, you have a question? Justin, it looks like you have your microphone on. Do you have a question? I guess not. And then finally, for extra credit, I said, what is the shear stress at point A? And what's the answer to that? Anybody? This was really a gift. This is 0 because pure bending only creates plane stress. It's just like torque only produced shear stress. So this was the answer for the extra credit. So now, I think you guys are in pretty good shape for understanding pure bending in one dimension. Okay. And what I'm going to do on Wednesday is I'm going to expand this. And the next two things we're going to do in this area are, no questions on this, right? I'll erase this. So the next steps are two-dimensional bending. Because all we've done as far as one-dimensional bending. And then we're going to look at bending with multiple materials. I'll probably give you one more quiz. And then for right now, my thinking is on the Monday of Thanksgiving week, you'll have nuclear material science exam number 3 on that Monday. in class. And it will be on bending, 1 and 2 dimensional, as well as looking at different materials. Just for your planning on that. Okay. Any questions on what I've gone over today for materials? Okay, let's shift courses here and let's look at reactor theory. And just to summarize where we've been thus far, we're at steady state reactor. And we know that implies that the rate of change with the neutron population with respect to time is exactly equal to 0. We developed equations for K infinity to find K infinity. And we know based on this, based on that value, is this fuels moderators mixture viable as a reactor core. We know we want K infinity to be as high as possible because we need to account for leakage to come up with K effective, and we need this to be hopefully greater than 1 and hopefully quite a bit greater than 1. Okay, so we did this for an earlier quiz to find K infinity. We then followed up to calculate buckling for any fuels moderators mixture. Along the way, we calculated the macroscopic cross-section for transport, which is related to the macroscopic cross-section for scattering. We calculated the macroscopic cross-section for absorption. We used those to define L, which is the thermal diffusion length. And the thermal diffusion length is the distance a thermal neutron travels before it's absorbed. We use those to calculate B, which was buckling. And that came out to be K infinity minus 1 over L squared. So when we found buckling, this buckling value is exactly this expression or equation. And it is found by looking at the fuels and moderator mixtures and all the earlier things that we calculated.
Can I interrupt for just a second? Because
Sure.
I just want to clarify, because I have in my notes that B squared equals K infinity minus 1 over L squared. So B is the square root of. Okay. All right.
That is, thank you.
All right. I just want to make sure that I
get ahead of
did it
myself.
correctly so far. Thank you.
So we've done that. Then, if there are no questions on that, We looked at leakage. We developed a term for that using J, which is the neutron current density. And the units for this, again, are neutrons per square centimeter per second. So the units are exactly like a flux. And remember, this neutron current density has a subscript. And what it looks at is a small window that is 1 centimeter by 1 centimeter. And it looks at the number of neutrons that travel perpendicularly through this little window per second to come up with neutron current density. So if we turn this little window sideways, if we're looking out here at the room as to what's coming in from the plus z-axis, and going through the window is what's going for neutron current density in the minus direction. We developed an expression for this. We then looked at taking it for all 3 dimensions. Because this leakage for neutron current density is occurring in all 3 directions, and these are vector quantities that are mutually orthogonal. So these are vector quantities that you have to vectorially add. Once we had that, we developed an expression for leakage, and then we developed the general diffusion equation. And that general diffusion equation was del 2 flux plus b squared flux is exactly equal to 0. This is the general diffusion equation. This is good for any size, shape reactor. Also good for any fuel moderator mixture. What we do when we have the general diffusion equation, we need a specific diffusion equation. So what we do is we have to find the del 2 mathematical operator for the shape of interest. So this del 2 operator will change for any shape you can think of. So the first one we started to look at the other day was for an infinite slab. For an infinite slab, my del 2 operator becomes d2 dx squared, because for an infinite slab, this is the geometric placement of all the materials. So this is the geometric boundary. This material goes to plus and minus infinity in the z direction. It goes to plus and minus infinity in the y direction. So the only variance you have is with x. So my general diffusion equation, by applying the correct del 2 operator to get the specific diffusion equation, becomes out now, whenever you have the specific diffusion equation, we solve this using initial and boundary conditions. In this particular instance, we know that the flux in this is going to have, if this is the center line, and this is where x is exactly equal to 0, the flux is going to have a parabolic shape. It is symmetric. It'll look something like that. We know that flux max is at the center line where x is equal to 0. We know that this distance is x of g, which is the width of the fuel and moderator mixture. Since this is 0, this side is plus x of g over 2. This side is minus x of g over 2. So this is the physical boundary, but the flux is not 0 at that boundary. It goes to 0 at some point beyond that. We call that the extrapolated boundary. And that dimension is x of 0. So therefore, this point is x of 0 over 2 plus. This is minus x of 0 over 2. This little point here is d, the extrapolation distance. It's the same on this side because it is symmetric. And looking at this, hopefully you can see that x of 0 is equal to x of g plus 2d. So this dimension is equal to this dimension plus d to come up with that. Okay. If you look at initial and boundary conditions, and your book did this for you, you know such things as the flux is equal to flux max at x is equal to 0. You know that the partial of the flux with respect to x is exactly equal to 0 because that's the slope of this guy at x is equal to 0. And they just randomly picked a boundary. So if we pick that boundary right there, and we look at the neutron current density that's going in that direction, which would be Jx minus. We know that Jx minus is equal to the flux divided by 4 plus d over 2 times the partial of the flux with respect to x. We know that this boundary, since there's no fuel and moderator out here, the flux, the neutron current density going in that direction is exactly 0. If we make this to be a triangle, this slope is rise over run. The rise is the flux that exists at the boundary, and it goes to 0. The run is little d. And when you utilize this in this equation, and you might, if you've been following this, this would be in your textbook on page 262. When you utilize this for your infinite slab, and you solved when you use your boundary and initial conditions, you came up with the flux at any point is equal to the maximum flux times the cosine of pi x over x sub 0. So we initially guessed that this is a parabolic shape, but in reality, this shape comes out to be a cosine. And if you substitute in x is equal to x sub 0 over 2, you'll find that this equation tells you that the flux at plus x sub 0 over 2 is exactly 0, which is what you expect. If you put in the flux at minus x sub 0 over 2, that's also going to equal 0 because it goes here. So you can find the flux at any point of interest. When you solved this equation and you looked at solving the specific diffusion equation for B, for an infinite slab, you found out that B squared is equal to x sub 0 No, there's two ways we can do that. Let me do it the other way. X sub 0 is equal to pi over B. Or, cross multiply here, B is equal to pi over x sub 0. If we square that, then we can square this side. And what we have just developed is the buckling for an infinite slab shape. So wherever you have an infinite slab, this is the governing buckling equation. This only talks, so this only addresses shape. But if you go back and look at what we calculated before for buckling, we know that for materials, fuels, moderators, the buckling squared was equal to K infinity minus 1 over L squared. So this addresses the materials. But this buckling squared is the same as this buckling squared. So whenever you find the buckling from just looking at the fuels and moderators, once you know what the shape is, you can say that the buckling you have found for that shape, which only looks at shape, is exactly equal. So we couple by B squared the shape to the materials. So for example, your sample problem in the textbook, which is on page 264, example number 3, shows you how you take the mixture that you had for fuels and moderators that we started back with carbon and uranium-235 and uranium-238. We developed K infinity, then we developed buckling. Now they're using this in the infinite slab to find out the dimensions involved. I had a quiz for you for today, due on Wednesday. I would like to have gotten maybe a little bit further today. I would like to have discussed, gone into cubes, but I think you can solve this quiz. So what I'm going to do is I'm going to send you the quiz. Okay, I just sent that to you. If you could open that up. Okay, if you look at the quiz, what I've gone back to is we're continuing on the beryllium U-233, U-238 mixture that we had before. So for 10 points, if we place this in an infinite slab, I want to know what is the physical thickness, X sub G, of our slab. If I tell you that the flux is 5 times 10 to the 15th neutrons per square centimeter per second, and it's thermal, and the specific flux is 5 times 10 to the 15th neutrons per square centimeter per second times the cosine of pi x over x of 0. I want you to tell me what is the flux at the particular point x is equal to minus x of 0 over 3. Also, what is the neutron current density at that exact point? That's for 10 points. And then for extra credit, at that point, x is equal to minus x of 0 over 3 is neutron current density going in the plus x direction greater than that going in the minus direction? Or is the minus direction bigger than the x plus direction? Or are they exactly the same? Circle one of the three and then justify your answer. This is not difficult, particularly if you follow the example in the book. I will be around here today, I'm sure, on this. We have interviews, and then we have a team session that's probably going to go from 5 to 6. But I'm sure I'll be here from 6 to 8 working on paperwork for this review. If you have any questions on anything, get back to me. I'll also be involved with the accreditation visit all day tomorrow, with the exit interview being between 3 and 4. And then I'll see you for regular class. Just some other things to mention very quickly. If you plan to withdraw from anything, the last day to withdraw is Friday this week. So hopefully you don't have to do that. If you are thinking of doing that, hopefully you'll chat with me before you do it. I still have 3 people that haven't registered for the spring yet. I did send you out the URI materials on Friday. I'll go over those with you either on Wednesday or Monday of next week. There's several of you that have not given me the waiver forms. I need you to present those to me or send them to me before we go on travel. And then I have other things that I'll pick up again on Wednesday. Any quick questions for me? Okay. If not, good luck on the quiz. My guess is it'll only take you about 10 minutes to do the quiz, particularly if you follow the example in the book. And I'll see you Wednesday at 12:30.